Okay, so let's jump back into it and do a couple more examples. Let's go ahead and switch back to our notes. And got probably about 3 more examples. Unfortunately, our break was a little long there. We got to talking about resources, catching up on past topics. If you were a little rusty on Calc 1 or haven't taken Calc 2 or retaking it after a break. So check those out. Hopefully it'll help you guys. Again, summer comes quick. We're hitting the ground running. We'll finish this topic today, and tomorrow we're starting in trig integrals. And then the next day we'll finish trig integrals and jump into partial fractions. So it's just techniques of integration, one a day at least. And let me go ahead and move my notes up. That reminds me as well. The one kind of problem with doing notes this way is sometimes I'll be writing and I'll be at the bottom of the page. So if I'm ever off the page, someone just chime in, tell me, let me know that you guys can't see it on the video. Sometimes I'm reading and watching my notes as I'm writing, of course, and can't not following the video entirely. So we want to do this next example, which is a little tricky, and I've heard it called the boomerang trick. But this is going to be a technique that you have to use when integrals don't get easier, or when integration by parts becomes cyclic. So we're going to try to integrate e to the x times sine of x. And now this one's a little weird because, well, we don't have a polynomial in there. Logarithms are another type of function where I can take derivatives of logarithms, right? And then when we get back our derivatives, we get rational functions. But here we've got these cyclical functions, e to the x and sine of x. And as I take derivatives and integrals, while we can do that really easily with these functions, they don't really change their nature, right? They still essentially remain the same. Of course, e to the x, we take derivatives all day, we get e to the x. Sine of x, we keep taking derivatives, we're going to get either sine or cosine back, and the minus sign switches. So it's not entirely clear which one should we choose. Well, let's just essentially guess and check. Let's just pick a u and a dv and go at it and see what happens. So if we have our u be e to the x and our dv be sine x, then our du is e to the x dx, and our v is going to be minus cosine x. And so we go ahead and write out our statement. Our original integral, e to the x times sine of x, is going to be equal to uv, so minus e to the x cosine x, minus the integral of v du. Well, okay, we changed around some things. We've got another integral, and the integral it's essentially of the same nature, right? We didn't really change anything about it. So, well, what can we do? We try again. And I do want to make a note that we want to use the same u and v. And I put same in quotes because, of course, they're not the same functions. But what do I mean by that? I mean, we used e to the x as our u in the first case, which means down here we have to use e to the x as u again. Because what's going to happen anytime you have to do integration by parts more than once, if you kind of flip around the nature or your choice, you will go backwards. So just real quick, if we go back to this one where we had our u be the polynomial, our dv was our e to the x. Great, that helped us this first time, but we still had to do integration by parts again on our previous example. If I would have chosen this 2x as my dv, right, instead of having my u as my polynomial, if I would have made dv as my 2x and then my u as e to the x here, it would take us backwards and get us back to the previous step. So we don't want to go backwards. Excuse me. Even if it doesn't look like it's getting simpler, you don't want to go backwards. So let's go ahead and write that out. Let me get a new piece of paper here. So we've got the integral of e to the x sine x is equal to minus e to the x cosine x plus the integral of e to the x cosine x. And so now what we want to do is integration by parts again with this guy. So we're going to have our u, we have to make the same choice, e to the x, and our dv as our cosine x. And again, when I say the same choice, I mean the same as in terms of where those functions come from. Cosine x came from that sine of x, and we made that sine of x our dv, so we now have to make the cosine of x the dv. Our du is e to the x, and our v is now sine of x. And so writing this all out, we've got minus e to the x cosine x plus, let's go ahead and keep our parentheses. We've got uv minus the integral of v du. So how does this help us? We've got minus e to the x cosine x plus e to the x sine x minus the integral of e to the x sine x dx. We've gotten back to where we started. And so while it looks like we're kind of just spinning our wheels and going around in circles, the key thing that has changed is this minus sign here. What we can do is we do have an equation, right? This formula is an equation saying that our original integral, e to the x sine of x, is equal to now an expression involving no integrals minus the original integral. So the trick is to essentially add this over. In other words, what you can kind of think of, if you want to do like a substitution, we had some integral. Let's call it I. And let's call it I sub x or I of x as that integral. And we said that I is equal to minus e to the x cosine x plus e to the x sine x minus itself. And so I can add that over, and what do we get when we do that? We get 2I of x is equal to minus e to the x cosine x plus e to the x sine x. And so now when we divide by 2, I'm just going to leave it as a factor of 1/2. And in this case, I'm going to do some simplification. It wouldn't really be necessary if you want to take that whole expression and divide it by 2. I'm going to go ahead and factor out the e to the x and then write it as sine of x minus cosine x. To me, that just looks like an easier way to write it. But again, other equivalent ways, if we're talking about in terms of factoring and what level of factoring you guys need to do, perfectly fine to have it. Something like that. So either of those forms, reasonably simplified, and they're not really philosophically much different in terms of simplification. Everyone see how that trick works? So as a check, take a derivative of this guy and see what you get. We should get back e to the x times sine of x. Okay, so we've got maybe 5 minutes. We'll see if we get one, maybe 2 examples in. The last thing I want to cover is just, and you know what? I should start. I need to start numbering my note pages so I can keep them in order. Let's do one more example of, well, what happens now when we have definite integrals? Not much changes. We just got to plug in the values at the end, right? And that does remind me, to be official, we need our plus c's on those guys. If we're doing definite integrals, though, we don't need our plus c's. We just got to plug in our limits. Actually, it looks like I have one page out of order. I'll deal with those after class and try to organize them when I take pictures and upload them for you guys. Look, I think we want to do arctan. Yeah, there we go. So how does this work when we need to plug in bounds? Let's do an integral of arctangent. From 0 to 1. So again, we don't have a product here. So the product is sort of hidden. We need a u and a dv. As we get going and as we get more practice with integrals, more techniques, especially come like quiz time and come exam time, you're not always going to be told what technique you need to use. So hopefully we'll get some time to review. And when you see things like that, again, there's a little bit of guess and check involved. You got to be able to think through some steps kind of in your head and think ahead to see if the techniques you're going to try are going to work out. So with something like arctan, at least the tools we have in our belt right now, something like U sub, you can look at this and kind of see, well, there's nothing to make a U sub out of it. So you would go through your next item on the list is integration by parts. And well, we think, well, can't integrate arctan, we can take a derivative of arctangent. And so if we check it real quick, what's the derivative of arctan? Oh, sorry, du. Another good thing to remember if it's been a while since you've taken calculus. Derivative of arctan, 1 over 1 plus x squared. And then v will just be x. So did this help us? Let's plug it in our formula here. We've got the integral from 0 to 1 of arctangent x is, we go ahead and write out the same formula, x arctangent of x minus v du. So x times 1 over 1 plus x squared dx. And then when we have definite integrals, you want to keep the bounds on the integral that we haven't done yet. And we're just going to have to evaluate this guy. So we want to think of this piece as already integrated. And so we often just put the evaluation line to remind ourselves from 0 to 1. The other thing you can do if you want to, get a little lazy with your notes, I see a lot of people doing this, is just wait till you're completely finished with all integration and then evaluate everything from 0 to 1. Perfectly fine to do it that way. Sometimes it's also easier, though, to do this one first, since all you got to do is evaluate it. A lot of times, especially when you plug in 0, it'll vanish anyway. And so if it vanishes, if it goes to 0, sometimes it's just easier to organize your writing without having to write that same piece every single time when you evaluate it. So let's go ahead and do that. Let's do this in parts. So we've got our x, arctangent of x, when we evaluate it. 0 to 1, I plug in 1, arctangent of 1, pi over 4. So we will get pi over 4, and then, of course, minus 0 just gives us pi over 4. So let's put that one off to the side. And now what do we have? We've got pi over 4 minus our integral of 0 to 1, x over 1 plus x squared dx. Now what do we got to do? We've got another integral to do, and we got to kind of go back through our checklist. I can't just straight up integrate that. We could try integration by parts again, but that might also be overkill. In this one, we can actually just do a u sub. So it'll give us a little bit of time to review that. Let's go ahead and make our u the denominator, 1 plus x squared. And then du is going to be 2x dx. So our integral is going to be 1/2 du, gives me the x dx, and then the denominator is u. In other words, we've got 1 over u du. And again, I'm not sure how you learned u subs. There's a couple different ways to do it. We could change the bounds in terms of u if we'd like to. We could integrate in terms of u and then back substitute. I like to change the bounds. So if we have 0 in for x, the bottom limit becomes 1. If I plug in 1 for x, top limit becomes 2. So easy enough just to change those bounds. And now we just want to evaluate that guy. So we will have pi over 4 minus 1/2 natural log of u. And then I guess we should say, let's put that in a bracket, because we only want to evaluate that u now. And so what do we got? Pi over 4 minus, Natural log of 1. Oh, I didn't write the right one.
Just off the bottom of the page, that line, the last one.
Ah, thank you. 1 to 2. So it looks like we've got 1/2 natural log of 2. And then what's the natural log of 1? As good calc students, you know it's 0. So minus 0 there. And so that's our final answer there. Any questions? All right. So that's it for today. Feel free to stick around if you've got anything you want to talk about. I can stick around for 5-10 minutes. Otherwise, I'll see you guys tomorrow. Tomorrow is Wednesday, so I'll also have office hours tomorrow from 3 to 5.
Those just drop in any time, or should we email beforehand with office hours?
Drop in any time. I should have the Zoom link open.
I have a quick question.
Yeah.
When are the lecture recordings typically posted by, like that day or the next day, or?
That is a good question. I will try to get lecture recordings posted this day. So usually like right now after class, once we get off Zoom, I will wait for the videos to convert from Zoom. And then I will try to both upload the lecture notes and the Zoom video into Zoom or into Canvas. So should be shortly after class. Yeah, like if you can't make this hour usually, or if it's better for you in the afternoon,
Yeah.
I'll try to post them as soon as I can right after class.
Okay, cool. Thank you.